Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This presentation examines some very simple CPU tests with the Arduino GIGA R1 Wi-Fi board. The GIGA R1 Wi-Fi is a powerful, feature-packed board with a dual-core microcontroller. The primary core is the ARM Cortex-M7. The secondary core is the ARM Cortex-M4. Although the second core is started from the first core, both cores operate autonomously. The tests in this presentation are limited to the CPU only. Future tutorials may examine other performance tests with the secondary components and accessories on the board. More importantly, none of the tests in this tutorial represent any benchmark performance. The identical tests run on different boards provide some basic or elementary guidance on the relative performance of the respective boards. The objectives of this tutorial are very limited. From a microcontroller perspective, it is indeed possible to gain an understanding of the relative speeds by running the same set of programs on diverse boards. Performance benchmarks can get complicated easily. It is best to keep it simple for the purposes of this presentation. Also, the Integrated Development Environment, IDE, or the command line compiler settings may have a role in the float and double data type calculations. Using both cores will become a natural exercise once the constraints are fully understood. For example, one of the boards in this suite of tests is the Sony Spresence board that has a whopping 8 cores. Naturally, for relative comparison purposes with the GIGA, we will use only one core for the tests. The underlying objective is to help you overcome inertia and to get started on the long road to practical computing with microcontrollers by ensuring that you are positioned correctly at the starting gate. Some key characteristics of the GIGA board are: the M4 will need some memory. The M4 does not output to the serial monitor directly. Multiple serial monitor sessions can be opened by the M7 host processor. The GIGA board has two cores, M7 and M4, which are binary compatible with each other. M7 is the main processor and has superior hardware features. M4 is booted from M7. The two cores can run separate sketches in parallel. It is not possible to do justice to all the features in this single slide. Please refer to the respective datasheets from ST Microelectronics because even Arduino is unable to provide basic information. To run a sketch on the Giga's M4 processor, a few extra selections are required. The flash memory split between M4 and M7 must be specified from the menu. The target core must be explicitly selected. The M4 session sends serial output using remote procedure calls that are intercepted by the previously launched M7 session and then displayed on the latter's serial monitor. The four basic tests in this tutorial are integer, long, float, and double. Since the integer and long word sizes are 32-bit, there should not be any significant difference in the elapsed times for the separate tests with the two data types for some of the boards. Please note that for any authoritative analysis, one would have to examine the compiler-generated machine instructions. Please excuse me for my inability and ignorance in doing just that. These tests are simple exercises using the IDE with default settings and standard Arduino libraries. It is important to understand that the Cortex cores are designed by ARM and licensed to STM Microelectronics, who designed and developed the dual-core microcontroller that the Giga board uses. One of the simplest tests for integer arithmetic is to perform the sieve of Eratosthenes calculations to find prime numbers up to a specified upper limit. In this calculation, all numbers up to the upper limit are flagged initially as prime. Then the iteration proceeds to calculate the double of each number up to the upper limit. These numbers are removed from the list since they are not prime numbers. This process iterates through all numbers in the list. All numbers that remain flagged as true are indeed prime numbers in the range. Then the iteration proceeds to calculate the double of each number up to the limit of 65,536. These calculations are repeated 1 million times to arrive at the total elapsed time. This repetition is highly arbitrary and can easily lead to dilution of test results, especially for floating point tests. It is understandable that the number of iterations selected to exercise the integer arithmetic may be considered an extreme choice, but perhaps the iterations will minimize any random effects over the duration of the test. The objective of this exercise is not to estimate any metric towards operations per second, but rather to measure an elapsed time period that can be used to compare across diverse boards that have different computer architectures, such as the von Neumann or Harvard, to access code and data. The results from running the same set of sketches on a variety of boards using the data type int for the arithmetic is shown on this slide. The vertical bar is the time required to complete the calculation by the respective boards. In other words, the smaller the height, the faster the corresponding processor is able to complete all the calculations. You can clearly see that the Giga board is faster than the other boards. Of course, within the Giga board itself, the M7 processor is faster than the M4 coprocessor. The M7 processor operates at 480 MHz, while the M4 core is pegged at 240 MHz. The results from running the same set of sketches using the data type long on the same set of boards is shown on this slide. The results are similar to the findings presented on the previous slide. It should be noted that some processors in these tests use the same number of bits for int and long. Their results did not change from that shown on the previous slide. However, once again, the Giga processors required the least amount of time to complete the calculations. The Mandelbrot set calculation is a simple way to run floating point calculations iteratively. In this exercise, the sketch calculates the Mandelbrot set several times. The calculations start at the center of the coordinate system, uses a nominal zoom value, ramps up the iterations so that the elapsed time is more than several minutes to reduce the impact of the parameters that are not interest for the limited purposes of this tutorial. The equation is a simple complex number calculation. Z is updated with each iteration, which continues until Z is greater than 2. There is an additional loop control variable, the maximum number of iterations. The results from running the same set of sketches on a variety of boards using the data type int for the arithmetic is shown on this slide. The vertical bar is the time required to complete the calculation by the respective boards. In other words, the smaller the height, the faster the corresponding processor is able to complete all the calculations. You can clearly see that the Giga board is faster than all the other boards. Of course, within the Giga board itself, the M7 processor is faster than the M4 coprocessor. The results from running the same set of sketches using the data type double on the same set of boards is shown on this slide. The results are similar to the findings presented on the previous slides. It should be noted that some processors may require fewer bits for float data types than long data types. However, once again, the Giga processors required the least amount of time to complete the calculations. Let us review the steps for running the sketches on the Giga board. There is no extra step required to run the sketch on the M7 core processor unless the M7 coprocessor had been specifically invoked in a previous step. The two key selections to run the code on the M4 coprocessor are the corresponding core selection and, of course, the memory split so that the M4 core processor can use some of the available memory. Since the M4 coprocessor cannot communicate to the serial monitor directly, it has to use remote procedure call library to send data to the host M7 core. It is practical for introductory exercises to have a very simple sketch running on the M7 core to receive data from the M4 coprocessor, which can then be displayed on the serial monitor. Since the Giga board supports multiple serial monitors, perhaps one serial monitor window can be dedicated for this data communication. Launch the M7 sketch first, then in the sketch that will run on the M4 coprocessor, perform due diligence checks for the board, select the flash memory split, and target the M4 core. Only then should the code be uploaded to the board. The M4 host processor uses the RPC library to communicate with the M4 coprocessor. The library is initialized as the standard RPC begin command, just like the serial communications, and then it awaits messages from the M4 coprocessor, and whatever is available in the buffer is sent straight to the serial monitor. The M4 coprocessor also relies on the RPC library to communicate with the M7 host processor. So in the initialization sequence, the RPC begin command is issued, and during the calculations, whatever it needs to communicate, it uses the simple print style statements to communicate with the M7 host processor. The calculations for the Mandelbrot sequence are illustrated here, and it's a very simple set of floating point calculations for two sets of complex numbers. The results from running the same set of sketches on a variety of boards is shown on this slide. There are three distinct levels, with the Giga claiming the top spot in terms of performance. Its performance for arithmetic are several orders of magnitude faster than the other boards for either of its two cores. The word size for the different types of arithmetic are relatively the same for one or two of the boards. Hence, the numbers did not change significantly for the suite of calculations. Please pardon the apples versus oranges comparison here, because the differences in the fundamental data types can add a level of confusion for comparative assessment of the boards. Detailed assessment of the libraries invoked for these calculations have not been examined. Please be wary of inferring absolute conclusions based on the tests in this tutorial. It will be interesting to evaluate digital signal processing with the Giga board once the custom libraries for this purpose are publicly available. This tutorial was a basic introduction to the performance of the Arduino GIGA R1 Wi-Fi board. Some simple arithmetic tests with different data types were performed. Given the consistency of the results, the Giga board does hold promise for compute-intensive calculations with its hardware features. Of course, individual scenarios may yield different results. That's all, folks. Please provide feedback in any which way you can. This presentation was prepared with assistance as noted on the slide. Thanks, Joe Jackie, for the suggestions. This presentation is the first one in series of the suggestions by Joe Jackie. My apologies if I have unintentionally omitted anyone or any resource in this list. A very big thank you to y'all. Come back to the channel again with your advice.